We have derived the current controlled voltage source using a MOS transistor and also analyzed it thoroughly in the small signal domain. Now we need to find a suitable bias circuit for it and complete the picture. Okay. The small signal picture of the current controlled voltage source is this. Vi and Rs, and this is connected between the gate and source of the MOS transistor. We have VGS, we have the load RL, and the resistance which realizes the trans resistance is Rm, connected between drain and gate. Now the source is grounded here. Okay, so it is more convenient to pick a biasing technique where the source is already grounded. Okay, now if you leave aside two of the biasing schemes which require an op amp, we have either drain feedback which looks like this, or source feedback which looks like that. Okay, clearly the drain feedback configuration appears very suitable for this. First of all, the source terminal is connected to ground. Now we have a resistance Rm between drain and gate. When we came up with the biasing technique, we had no specific requirement, so we just connected the drain directly to the source, but it doesn't have to be like this. We can always insert a resistor in this branch and nothing will happen because the gate current is 0 and the biasing will not be disturbed at all. Okay, so this is suitable for this, and actually the resulting topology looks very similar to the common source amplifier with drain feedback bias. So we will use this biasing technique. The only thing we have to change is that between drain and gate we can't make a direct connection, we have to connect a resistor Rm. That's all that's there to it. Okay. So we have the supply voltage and a current source I0. Okay. And we connect this resistance Rm like that. And as usual, the input source is AC coupled through a capacitor C1 and the load is AC coupled through a capacitor C2. Okay. So this is the complete picture of a current controlled voltage source, and it looks exactly like a common source amplifier with drain feedback bias, except here we show a current source in parallel with a resistance because it's a current controlled voltage source. As long as this resistance is there, you can also equivalently show it as a voltage source in series with a resistance. Okay, so it's exactly the same circuit. The only difference between this and the common source amplifier with drain feedback bias is in the value of Rm, okay, and the constraints. In case of common source amplifier using drain feedback, the value of Rm is made very large, whereas now it's not so large. Okay, so this circuit is very simple and I don't think I need to discuss this any further. You can evaluate the operating point of this. You can write the small signal picture assuming C1 and C2 are shorts and find the gain. We've actually already done that. Now the only thing remaining is to figure out the values of C1 and C2 such that they do behave like short circuits. Okay, and for that it's very easy. I'm not going to go through all the steps, but you have to realize that the resistance looking that way between this point and ground is nothing but the input resistance that we've already evaluated. Okay, we know that this is RL plus Rm divided by 1 plus GMRL, and of course in this it is implied that C2 is chosen correctly so that it behaves like a short circuit. And similarly, the resistance that looks back this way is R out and we know that it is Rs plus Rm divided by 1 plus Gm Rs. Okay. So what is the condition for C1? You can see that if you deactivate the circuit across C1, you will see Rs plus Rin. Okay. Inside the circuit we have Rin, and C1 is connected here, Rs is connected there to ground, and this is ground. So across C1 you have Rs plus Rin. So the reactance of the capacitor C1 must be much smaller than the resistance that is across it, or C1 must be much more than 1 over omega, where omega is the signal frequency, times Rs plus Rin. Okay. And similarly across C2 you see RL, and you see the output resistance of the circuit, which is Rout. So C2 must be much greater than 1 over the signal frequency omega times Rout plus RL. Okay. So you see RL on this side and you see Rout on this side. So C2 must be much more than that one. Okay. Now we can also realize this current controlled voltage source using source feedback bias. Okay. Again, the signal picture of the current controlled current source is this. Okay. And if you use source feedback technique for biasing, we will have I0, we have the supply voltage, and we have some fixed voltage Vg0. Okay. This is not the most convenient bias circuit for the current controlled voltage source, but just to see how it is done, we can do that. Okay. First of all, the drain here is not connected to small signal ground, whereas here the drain is connected to VDD, so which means it is the small signal ground. Okay, so that is one problem. And then, but we have dealt with that kind of situation before. And then here the source is not at ground, whereas here the source is at ground, so that has to be fixed as well. Okay, so let's do all of that. First of all, this Vg0 has to be derived from the supply, so we use our usual resistive divider to do that. Okay. And then the input has to be connected to the gate without disturbing the bias. So as usual, we use AC coupling. We cannot connect the drain directly to the supply voltage because that will short the drain to ground in the small signal picture. So we have to connect it through a bias resistor RD as usual, and also the load resistance has to be AC coupled to the drain node. Okay, so let me call this C2. Then finally we have to have a resistance between gate and drain in the incremental picture. Again, of course, everywhere we have assumed that the input signal is at some frequency greater than 0. That is, it's not a DC input. So we have to connect it between drain and gate, but we shouldn't connect it directly because that would disturb the bias. That will actually introduce drain feedback. So we AC couple that as well. We connect a capacitance in series, but the idea is that this capacitance behaves like a short at signal frequencies. So for signal frequencies, it's as though only Rm is connected between drain and gate. So this is Rm. Okay. And finally, the source terminal has to be grounded, and we know how to do that. We have used it for common source amplifiers. We can connect a capacitor to ground. Okay. So we have 4 capacitors, but that's okay. So this is just to show that you can use the source feedback bias also for the current controlled voltage source. Okay. So let me draw this a little more neatly. This is the input source. It's AC coupled to the gate of the transistor. From the source we have a current source I0, which is bypassed to ground using another capacitor. We have the drain bias resistor RD and resistance RL. This is the supply voltage VDD. And finally, we have the resistor that realizes the trans resistance Rm in series with a capacitor. So C1, C2, C3 and C4. C1 and C2 we have already evaluated. C3 is similar to what we needed for the common source amplifier. C4 I won't do it now. You can take it as an exercise and do it yourselves. There are 2 extra components here. We have R1 and R2 from the gate to ground. Okay, so that is we have R1 parallel R2 between the gate and ground. First of all, by choosing R1 and R2 to be very large, much larger than RS, you can completely neglect the effect of it, because if R1 and R2 are much larger than RS, the effective resistance between gate and ground will still be RS. Okay, if that's not possible, then wherever you had RS before in your expression, you have to change it to R1 parallel R2 parallel RS. Okay. Also, we have this drain bias resistor RD, so that introduces an additional resistance from drain to ground. So wherever we had RL before, it has to be replaced by RL parallel RD in our analysis. Now in practice, it's not difficult to make R1 and R2 very large so that they can be neglected, whereas it's not quite possible to make RD very large, because in that case the voltage drop across this becomes very large and you have to use a very large supply voltage. Okay. So this will affect the circuit to some extent, but because it's a current controlled voltage source, the output voltage should not depend so much on the load resistance, so it will be affected but not by much, as long as the transconductance GM is very large. Okay. So this is a current controlled voltage source with source feedback biasing. Okay. So that completes the picture of the current controlled voltage source, and we've also illustrated that we can combine it with the 2 biasing techniques, drain feedback and source feedback. Okay.